Hello friends, once again welcome back to Alchemy Academy platform. So today in this tutorial I'll discuss about laws of radiation. So what I'll discuss here, I'll discuss about laws of radiation. So this is basically the continuation from our previous tutorial. In that I was discussing about the radiation heat transfer. So back to this tutorial, I had told you about introduction about radiation heat transfer. Then I had told you about what is black body radiation, what is monochromatic emissivity, and what are the properties of radiation. All these things I had told you in my previous tutorial. So now in this tutorial we'll discuss about laws of radiation. So in that, first topic that I'm going to cover is, first one is Stefan Boltzmann law. Stefan Boltzmann law. Now the second law that I will discuss is Planck's law. Planck's law. Now the third topic that I'm going to cover is Wien's displacement law. Wien's displacement law. Now the fourth topic and the fourth law that I'll cover is about Kirchhoff's law. Kirchhoff's law. So we'll discuss one by one. So first of all, let's discuss about the Stefan Boltzmann law. So according to this law, total emissivity power of a black body is proportional to the fourth power of the absolute temperature. So this is the emissivity power of a black body, and it is proportional to the absolute temperature raised to the power 4, and this proportionality constant is known as the Stefan Boltzmann constant. Correct? So EB is your basically is the energy radiated per unit time per unit area by the ideal radiator. So this is the Stefan Boltzmann law. Now we'll discuss about Planck's law. So according to Planck's law, it describes the spectral density of electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature when there is no net flow of matter or energy between the body and its environment. So this is your Planck's law. So in Planck's law, what happens? The distribution of energy in the spectrum of a black body is known accurately. So in Planck's law, we can get to know the distribution of energy into the spectrum of a black body accurately. So it is given by Planck's law, and this is the value EB at a lambda is equal to WB into lambda. This is the just symbol. Somewhere it is written as EB dash lambda, somewhere it is written as WB dash lambda. So this is your basically emissivity power of a black body at a given wavelength lambda, that is equal to 2 pi h into c square into lambda raised to power minus 5 divided by e raised to power hc divided by k into lambda into t minus 1. So where c is your speed of light, h is your Planck's constant, lambda is your wavelength of light, h, the value of h is basically your 6.626 into 10 raised to power minus 34 joule second. So this is the value of Planck's constant. So WB lambda here is monochromatic emissivity power of a black body. So this is the summary about the Planck's law. Now we'll discuss about Wien's displacement law. So Wien's displacement law states that the black body radiation curve for different temperature will peak at a different wavelengths that are inversely proportional to temperature. Correct? So you see it, you can see it here, the definition. The Wien's displacement law states that the lambda max, the value of lambda max that we get by the emission of a black body is proportional to its absolute temperature at which it has been subjected. So just see the law. Now let's see the diagram here. This is the emissivity power by a black body, monochromatic radiation lambda. It is on the y-axis, and here wavelength is on the x-axis. Okay. So this WB lambda versus lambda max has been drawn at two different temperature. So at temperature T2 it is lambda max T2, and if you draw the value we'll get this value. Now at a temperature T1, this is lambda max T1, and the value we get here, this one. So as we know that the value of T2, since T2 is greater than T1, it means that here you see the from the graph, lambda max T2 is lesser than the lambda max T1, because this is the wavelength here. At T2 is higher temperature, but lambda max here is lower than the lambda max at the value of the temperature T1, correct? So lambda max T2 is lesser than the value of lambda max T1. So lambda max is basically your inversely proportional to your absolute temperature. So this is basically lambda max into T, it becomes constant. Now the value of constant is lambda max into T is equal to 2.9 mm into Kelvin. So this is called your Wien's displacement law. So if there are two bodies are given, then we can solve as lambda 1 max into T1 is equal to lambda 2 max at temperature T2. So if any of the three is given, other fourth value can be calculated. So that's what it has been written. Lambda max at T1 into T1 is equal to lambda max at T2 into T2. So this is the Wien's displacement law. Now we'll discuss about the Kirchhoff's law. So you just will understand it here theoretically. So by taking an illustration. Now suppose that a body is placed. Now let's take a body is placed inside the enclosure and is allowed to come into the temperature equilibrium with it. So here one body is there, this is the first body and this is the second body. The first body, this body, sample body has been enclosed into the black body enclosure, correct? And it is allowed to come into the temperature equilibrium with it. Okay, so at equilibrium the energy absorbed by the body must be equal to the energy emitted. So at temperature equilibrium, obviously if temperature remains constant, then the amount of energy that is being absorbed into the body must be equal to the amount of energy that is being emitted from the body. So Qi into A, alpha is your absorptivity. So Qi into A is your amount of energy that is being absorbed, alpha is your absorptivity factor. So this is the net amount of energy that is being absorbed by the sample, this body. And what is the amount of energy that is being emitted is E is the amount of emissive power of this body into area. So this is the amount of energy that is being emitted from the body. So E is equal to Qi into A into alpha. Now if we now replace the body in the enclosure with the black body, so just replace this body with the black body of same size and shape and allow it to come into the equilibrium with the enclosure at the same temperature. So for that case what happens? Instead of E it becomes EB, A becomes same, Qi will become same, A becomes same. Here absorptivity would be becomes 1 because it is now black body, correct? So if you divide E divide this equation 1, suppose this is the equation 1, this is equation 2. So equation by equation 2 will get EB divided by EB is equal to, this will get cancelled, will get alpha value. Okay, and as we know that since E by EB is your emissive power of the black body, so we got alpha is equal to epsilon. So any body which is having the value of alpha is equal to emissivity, means absorptivity equal to emissivity, then it is basically your Kirchhoff's identity. So if the value of alpha is equal to epsilon is equal to 1, then it is called as black body. This is black body. But if alpha is equal to epsilon not is lesser than the 1, then it is called as gray body. So now let's see Kirchhoff's law. So this is applicable to all bodies. So according to Kirchhoff's law, at a temperature equilibrium, that was I had told you earlier, the ratio of total radiating power of any body to its absorptivity depends only on the temperature of the body. So this is the Kirchhoff's identity. So we can write this one as, consider any two bodies in temperature equilibrium with the common surrounding. So this is the body 1, this is the body 2, and it is in the temperature equilibrium with the surrounding 2. Then in that case, W1 divided by alpha 1 is equal to W2 divided by alpha 2. Alpha 1 and alpha 2 your corresponding absorptivity value. So W and W2 is your total radiating power of two bodies, bodies 1 and body 2 respectively, and alpha and alpha 2 is your absorptivity of two bodies respectively. So this law is basically applies to both monochromatic and total radiation system. Now like I had illustrated earlier only, if first let's assume that first body is black body, in that case alpha 1 is value is 1, then for that w1 divided by alpha 1, so this value becomes 1, so we got w1 equal to w2 divided by alpha 2, and it is equal to wb, this is because black body. So we got what we got, alpha 2 value we got w2, if you take alpha 2 this value, then it becomes w2 divided by wb, so we got the alpha 2 value, and this is equal to your emissive power of a, and this alpha 2 becomes, this is a epsilon 2, so we got here alpha 2 equal w2 equal to alpha 2 into wb, so therefore alpha 2 becomes emissive power. Okay, so alpha 2 equal to E2 is equal to alpha plus epsilon, alpha is equal to epsilon, this is called gray body. That's what I told you in my previous, just back to two slide back. So alpha is equal to epsilon, it is lesser than 1, is called as gray body, and alpha is equal to epsilon is equal to 1, this is called black body. So any body which is placed in black body atmosphere can be considered as gray body, hence this is true and this is applicable. Now note down, these are some theorems or points that is valid with respect to the Kirchhoff's identity. So when any body is at temperature equilibrium with its surrounding, its emissivity and absorptivity are equal. So both values are equal, and it is lesser than 1 for the gray body, and if it is greater than equal to 1, then it is for black body. Now except for black bodies or gray bodies, absorptivity and emissivity are not equal. You must remember this point. If the body is not in thermal equilibrium with its surrounding, so alpha equal to emissivity is equal to 1. So this is for black body. This is for the black body, whether the radiation is monochromatic or total, it doesn't matter. So this is applicable for the black body. So guys, that's all for today. This is all about the laws of radiation. So guys, thank you so much. In case if you have any doubt, you can comment in the comment box. I'll definitely clarify it there. So thank you.